Now, first agenda today is that I once again want to emphasize that those groups who have not submitted their project, please do it by today. At the minimum what I want is, that is the only thing I need, is an email from anybody in that group. If the group itself is in a bit of a confusion, do not worry, that we can resolve, at least most of the people in the group are. Copy all the members of the group and then say, this is the topic, this is the reason we chose the topic, that is all I require. You do not have to get any more detail, because from now till the completion of the project report, I am going to spend time individually with groups to take you through the various steps, because all the clarifications, questions, what to be cover, what not to cover, all that we will do later. But to begin with, I just need to know the topic, why you chose the topic. Why you chose the topic is very important, spend some time on this, because at the end of the project report, when you read through the report yourself, you should be able to look back and say, that is the purpose in which we got into this project, did we achieve that purpose. The project itself is not all that important, because let us say you are writing about a project about a particular chemical, how well that chemical report is written is only part of it. I just want to clarify your mind, you went into that with a purpose, did you cover enough ground to meet the purpose. So, that is the reason I am asking for that thing there. You can write initially, during the course of the next 1 week you can also slightly modify, because it is not one shot there is no point of return, that sort of a thing is not there, you can. So, feel that is the first thing I wanted to make. Secondly is, in today's topic I wanted to cover something about green hydrogen, but I realized one of the groups just sent me a mail saying that they are interested in that topic. Therefore, it will be very difficult for me to continue with that topic. So, I will just keep that aside. It will be like sort of, if two different people choose the same topic, there is no problem at all, because you do not have to be exclusive, like you saw in research or in companies, there are many companies working on the same kind of a product chemical, that is fine. So, it is just how you attempt what we have learnt, that is what is the key. So, any topic is good enough, if it is a repeat, no issue at all. So, with that what I am going to do in today's class, I am not going to talk about this hydrogen thing, because it will be like letting the just open it out the whole thing and talk to one group, whereas the other group will not have that advantage. So, instead I am going to talk about two things. Before that, like this project thing, one more very serious recommendation to you, in fact I urge you to do this. I do not think any of you would have attempted to take up the previous lectures. I left two things open, right. One, solar thermal desalination, I mentioned and left it like that. Then I said Vayujal, just briefly at least on Vayujal and left it. Pick any one of them and do the calculations yourself, it is very important to learn. Otherwise, it is like swimming or cycling. Swimming is very simple, body bulk density is very similar to that of water. So, in theory you should not drown. Secondly, okay, now that the theory part is very clear, that if you put into water, your density and water density are more or less the same, so you will not drown. The swimming is, take a breath, put one hand forward and kick the leg and so on. Now, are we finished on swimming? Can we go to the sea? This is like that. So, the whole purpose of this type of a courses is not to see conceptually whether you are clear or not. I take it for granted the fact that you have come here, you are conceptually very good. Also, based on the feedback from many companies who have recruited people, they always say one thing, they have never said these guys are not conceptually strong, not from I think people like your background. Always the complaint has been they are not industry ready. So, which means understanding concept is very clear, but when we are asking them to work on a particular problem of the company's interest, somehow we are not very satisfied with what they do. So, that is the main refrain. So, if that is the case, till now you have been listening, interacting, I am very sure you are understanding the concept, but it can be a false security. Unless you put your hand like the swimming or the cycling example I said, it will not stick inside you. So, I think it is worthwhile, do spend the time, it will take some time, it is worth spending the time, and I think you have the time. I can't believe that you do not have time to do. in spite of your other courses, in spite of, you must allocate time for this, pick up either Vayu gel or the thermal thing, go through this calculations. What do you mean by calculation is that draw the flow diagram as you think the scheme is, and then after you draw the flow diagram, try to estimate the input output, because then only it will give you the variable cost. Hang on, what the variable, then try to figure out approximate sizes and the types of equipments required, approximate, still you can do with flow diagrams. Then it will give you a feel how much will it cost, because these two questions, what is the cost of a product to make, what is the cost of a plant to make the product is the key. So, this thing will come only with practice. So, do take that Vayu gel or thermal desalination. In my class notes which I put on Moodle, there is some hyperlinks I have given to some sites. You can go through the sites, it gives you the starting point, and then I feel that if you do that, at the end of it you will realize lots of things about technology, about people's motivation and technology, what is actually sincere technology development, what is blah blah blah, everything is available in these two examples. So, do spend some time and do that. Okay, we are 5 minutes into this lecture. So, in this class what I am now going to do, dropping this thing, I am going to talk about this off the cuff I have come, because I realized this when I half an hour before that people have sent me request, I want to work on this project. So, this is something which is I have worked on this topic. It is an example of a failed technology development. So, I developed this technology, I am very proud of that, but it was a failure. So, I am good. Failure means finally the objective of technology development is to develop, sell the technology, build the plant, like that, did not happen. And not because people were not willing to buy or that, because inherently what we developed is, so that is what it is. So, I have some experience, I will just quickly go through that. The background to this is, this product is called Polysilicon, and Polysilicon is technology development is what I was involved in this. Some of them I will go through quickly, because anyway I am going to put it on Moodle. Looking for saying that lots of interesting data will be there, why these guys failed, keep looking for it. I will also tell wherever it is appropriate. First is polysilicon is a pure form of silicon, Si. It is called polysilicon because silicon can also come in a crystalline form, like carbon is in various forms, right, amorphous carbon, carbon if it is crystalline it is diamond, carbon in 2-dimensional is graphene, and so on, like that. So, like that, if silicon similar to carbon, because it is also tetravalent, it is not completely crystalline, but it is pure, which means it is predominantly Si, very little impurities other than Si. That is called polysilicon, because it is available in the form of several crystalline matter randomly oriented. So, it is not a pure crystalline material, it is a kind of a mixed up. So, that is the name polysilicon. The use of this material is, if it is a extra pure grade, I mean the highest purity grade, it is used in semiconductors. All the chips that we talk about, the base is the silicon, and then you dope it and get transistors, and then into microprocessors, into whatever it is. So, entire electronics semiconductor industry requires ultra pure silicon. So, that is one big use over that. If it is not all that hot quality meaning in terms of purity, basically it is purity, and purity will be expressed in parts per trillion atoms, not part per million, parts per trillion atoms, that is the kind of a purity levels we are going to talk about. And if it is not that kind of a purity material, it can still serve the purpose in photovoltaic industry. So, all the silicon cells in many of our rooftops which you see, silicon rooftop, this is used there. So, it has got two very high value application and reasonably high value application polysilicon. Now, you all know about what is semiconductors, right. So, I would not go into that. It semiconductors is something which, unlike metal whose band gaps are so close to each other, for all practical purposes electrons can simply float around everywhere, therefore, they are very good conductors. Semiconductors have fairly wide band gap. So, either the electron is here or it is there, nothing in between anyway. So, it is like not fully conducting, at the same time it is also not a non-conductor. So, that is why it is working in semiconductors and electronics. The band gap, which is the one that we say between the two levels, is 1.1 electron volts. EV is electron volts, that is the silicon's band gap. Now, you know, electromagnetic radiation is a source of energy. So, electromagnetic radiation can be described either in terms of the frequency or in terms of the wavelength, because if you know it goes the speed of light, if you know frequency you can calculate, or you can convert it back as a energy unit in electron volts. So, in case of silicon, it has a band gap of, like I said, 1.1 electron volts, equivalent to 1080 nanometers of wavelength. What it means is that it is kind of at that energy level and above, silicon atoms will get excited, electrons will jump from one band to another band. So, that is a property of silicon. Now, we switch to photovoltaic. The whole application is, I am not going to talk, one part of the application I will leave beside, which is the semiconductor I will leave beside. We will talk about PV. Then we have to talk about sun radiation and things like. So, this is the graph which is taken. It gives you the energy distribution of solar sunlight, which means how much of energy is content and how is it spread across the wavelength, because you know solar sunlight as we get it is not a single frequency, it is not a single wavelength, it is not monochromatic, it is kind of various. So, this gives on the x axis the wavelength in nanometers, and on the y axis is the energy density. You can see the units, it is watts, which is the energy per time, watt per meter square per nanometer. It is a funny description. Watts per meter square is clear, that is in a given surface area how much energy is falling per second is watts per meter square, watt itself being joules per second. So, how many joules per second per meter square it is falling sunlight, that is clear, but that is a sum of all the contributing frequencies. So, this graph differentiates it and gives you a graph. So, if you integrate this across from 250 to that, you will get the total energy. Now, the total energy is a horrendous looking graph, but do not worry about that, the principle is the same. So, if you do that, then you will find that the total energy across this, across the entire spectrum here is depends from position to place to place. So, it is usually taken our kind of a close to equator kind of a place, you can take it as a maximum of about 1000 watts per meter square, 1050, 980. So, 1000 watts per meter square is an average that you can take for our kind of locations there. Now, the other okay. See, it is like this, imagine the sunlight is falling at this location, we go outside and imagine you have a device which will measure the energy content. So, you take a 1 meter square area and want to know how much of energy contained in the sunlight is falling in that 1 meter square area. Of course, the energy is continuously coming. So, the unit should be energy per time, because if you waited for more time you would have received more energy. So, the first unit is you are measuring is energy per time, which is what is watts. Then it is also per unit area, because if you put a large area you will collect lot of energy. So, watts per meter square, up to that you are very clear. This is the total of the sunlight itself is not a single frequency, single wavelength. So, it is contributed by various wavelength. The total is what you have measured. Now, I am trying to figure out the total, how much is contributed between this frequency to that frequency, how much is contributed between. So, I am doing a differential analysis. So, that is this graph, it says, let us say at this is the visible range between this frequency is what eyes can see, right. In that visible range, how much of energy is contributed out of the total. So, first we have to know the total. Total is the area under the curve, because if you take this is y dx, integrate 0. So, y dx, what happens, x will get cancelled, right. So, this nanometer to dx will get cancelled, what you will get is watts per meter square, integrated from low wavelength to high wavelength is the total. So, this area under the curve will be approximately 1000 watts per meter square, that is the meaning. So, the total energy that hits a unit surface area normally is around 1000 watts per meter square, one conclusion. But of which how much is contributed with various frequency, exact curve is like this, but now we will take, I am giving visible range what eyes can see. Visibility is this frequency is what eyes can see. Below that wavelength is infrared, above that above the wavelength is infrared, below the wavelength is ultraviolet. So, this portion is contributed by the ultraviolet. So, ultraviolet rays, you have heard about people wear sunscreen and all that. So, this is because of the ultraviolet rays, and the infrared waves is here. The key point to notice is in the previous slide, what is this sudden graph doing to do with polysilicon? Polysilicon, I said, is something which absorbs energy at 1.1 electron volts. So, 1.1 electron volts also I said what is the 1080 nanometers. So, this wavelength it will absorb, any wavelength lower than that also it will absorb, because lower wavelength means higher energy. It should have a minimum of 1.1 electron volts, it will come, but if it comes as let us say 1.6, 1.1 will be absorbed, balance will not be absorbed. If it comes as 2.1 equivalent electron volts energy, 2 photons will be absorbed. This is the Max Planck's, Einstein, they all said energy is quantized. It is as if pockets of energy are travelling, even though it is described in an electromagnetic wave form. For this purpose, you can assume that as if it is like a particle with 0 mass. So, that kind of a funda. So, the purpose of this graph is, leaving great physics behind us, is to say in photovoltaic cells, the theoretical energy that the sun can give to a photovoltaic device will be approximately 1000 watts per meter square. That is the one con. Out of which how much will it actually absorb will be this portion it will absorb, this portion it will not absorb. That point is very clear. So, what is this area as a function of the total area? If you calculate, it will come to about 30%, which is why it is said that any photovoltaic cell like silicon based photovoltaic cells, the maximum achievable efficiency ever on theoretical basis cannot be more than 30. Simple. So, that is the purpose, keep that in mind. Now, what happens is after you get this silicon, pure silicon is doped with N type impurities and P type impurities. What is N type and P type? N type is where there is a higher valency, things like aluminum, and silicon is valency 4. Take any phosphorus, 5 valency atoms you add. So, you have got one extra energy level added. In same silicon, in another portion you dope it with boron and things like that, which is trivalent. So, there is a shortage of energy levels there. So, with this you get a PN junction. Same, now the silicon has become coated on one side with P type impurity, coated on one type with N type impurity, very controlled, very small quantities. Then it becomes actually a useful device, because electrons, if they have to be, energy has to be created, you have to have some discretion level. In a metal, by shining you will not be able to get any electricity, because it is all over the place, the electron. So, you do not get the energy gap. So, that is a funda. It is found that a silicon device, accordingly, if you take a cell of this type, if you shine sunlight on it, it will give you 0.7 volts across the terminals. Now, theoretically it should be 1.1, because that is the band gap, but because of the losses and things like that, it will generate only 0.7 volts, and only 20% of the incident energy is converted against the theoretical maximum of 30. So, these are the two numbers. Now, a photovoltaic cell is typically made in the form of 150 mm square. It is like a very thin sheet. I will show you in the next picture, 150 by 150. Why 150 by 150? Why not 200 by 200? There is a bit of a reason there. So, 150 is the most common reason there, and it is 180 micron thin, very thin stuff. The picture is here. So, if you walk up to the very of the roof floor things and take a close look at it, all these guys will be sitting next to each other in that big panel, enclosed inside moisture resistant, dust resistant, blah blah blah. This is the fundamental unit. So, this is the silicon cell, and all these lines which you see, vertical and horizontal, these are actually small grooves cut on the surface, and then a silver paste is filled in that groove in order to conduct the electron. So, now imagine this is the one, it is sunlight is falling on top of that, it will stimulate electron hole pairs, and the electrons will jump on, get collected by this silver conductor, thin ones, very thin ones, and be available at the back end behind this. This is the front surface, the back surface there will be a contact that will be it connect the circuit. So, the potential difference between this surface and the back surface is 0.7. So, that is what it is. You connect a whole lot of them in series parallel combinations to get whatever you want. And if you can keep on connecting them in series, 0.7 volt, 1.4, 2.1, like that voltage adds up, the same current flows through all of them. Typically then what they do is that 60 such cells, again these are industry practice, you can cherry the numbers, there is nothing great about why 60, why 80, but just take a typical one. 60 cells in series if you connect, you will get 60 into 0.7, right, each cell is, so you get 60 into 0.7 is 42, whereas in that is under again thermodynamic kind of thing, 0 current passing through. But when the current passing through, I square R losses also will come. So, practically this kind of a modules will get 30 volts and 230 watts. Now, if you put 230 watts, I have to explain, it is very easy. If you take those 60 cells of that dimension 150 by 150 I said, try to arrange them 60, 60, 60, 60, in some configuration you can have. Normally, you do not put all of them in a straight line, you have some L by D ratio, you can choose any one of them you want, connect them, then you will get the total area. Practically you will get 150 mm into 150 mm is the area of one cell into 60, that is all the area you will get, some space in between will be wasted because you can't have. So, with that area, how much of sunlight falls on that, if you take it as 1000 per watts per meter square and take 20% efficiency, you will get 230 watts. So, that is the funda of this. Now, look at the value chain, again focus on PV value chain, we are leaving semiconductors. What happens is, start with polysilicon, this is the pure material, and then you crystallize it. There is a process called crystallization, because like I said, polysilicon is lot of crystalline material randomly oriented, there the losses will be very high. So, if you make them crystallizing, how do you do that is that you heat and cool in a very controlled manner, they recrystallize into regular crystals. So, it becomes crystalline silicon, just a process of heating, melting and very slow cooling, and then you cut those into small wafers and then you dope it front side, back side, then you prepare the surface, add all this silver paste connectors, put them into a module in an aluminum cage with glass, sealants, conductors, cables, all that, you have got this stuff, and then many of them connected together will get large DC power. Of course, transmission is always AC. So, you connect the DC to AC, you will have a transformer and then protective gear, so that all that sort of thing, that is the whole value chain. Now, first I will switch back to here. Now, what is the context? Why are we talking about all this? Because this failed project means you should know there is a project. So, what is this project suddenly became is, our group when we were working for a company, all this funda was given to us. India has 375 gigawatt of installed power. You can read up the Ministry of Power website, these are all figures from there. World so much, so India is 375. Then we said most of our power plants are coal based, some of them are hydro, some of them are nuclear, some of them are gas, very little of them are gas, because India has no natural gas available. So, mainly coal and so on like that. We said we will get committed to global warming initiatives, and therefore, all our we can't drop our existing power plants, but we will now sort of try to put newer power plants in the form of solar energy. So, that was a, then again 375 gigawatt installed, at least 1/3 should be solar. This was the target during the period. So, 375, 100 gigawatt. Now, suddenly you will find one small subscript 100 GWP that comes. Unlike normal power plants where the power rating is more or less same throughout the day, coal based power plant, if you take the rating, more or less the output remains the same 24 hours. The only place where it will drop down is when there is no demand. Let us say daytime, night time there is a variation. because usually daytime companies are working, lots of things are happening. So, daytime summer especially ACs are running. So, lots of, so between the daytime and night time there is a small demand variation, and since electricity you do not normally store, accordingly the power plant output will coast like this, but this variation is like that. Whereas, solar thing, if there is sunlight only there is power. So, anyway whatever you do between daytime and night time, it is can change from up to 0, and even during the day it can change like this, because the sun intensity starts in the morning, reaches a peak and then drops down. So, this 1000 is an average, but it is a highly variable average. So, what we do is that when we design a solar power plant, the peak capacity is taken for design purposes. It is not as if the actual capacity all the time will come from there, unlike power plants of other types where more or less they will come. So, this is a very important factor for cost calculations and all that we have taken into account. So, peak is taken, which means if 1000 watts per meter square sunlight hits it, then what is the power that will be produced is a peak power, clear. So, that is it.
So, this peak capacity will be at some point of the day, it is not actually saying that it will be for the day.
It will not be for the duration of the day, it will be designed on the basis of if
maximum it can
maximum. So, that peak maximum is what is shown as on this. Now, if you take the point is, now we are going to polysilicon project. So, where is this big picture to polysilicon project is coming? If you have to have solar plants of that type, you should know how much of polysilicon is required to build those cells. That is where we come from, right. So, the number is, if you want to have 1 gigawatt peak power solar plant, 400 tons of silicon is required. This number right now you can take it, but if you are so keen, why do you say 4000, why is it not 2000, why is it not 5000? Then you have to go to the earlier slides and say what is the size, what is the thickness I have got, then peak capacity, work backwards, you can get the power per cell, silicon used per cell, because if you know the dimensions of the cell, you can calculate what is the quantity of silicon required, right. So, 1 multiplied by that you will get it. So, it will come to 4000. So, you can imagine if 100 gigawatt power is what India is going to build, and each gigawatt power requires 4000 tons, there is a lot of silicon that is required to set up this plant. And at that point of time in India, and even to this day, there is 0 manufacturing for polysilicon. So, here was the so called opportunity, technology development and so on like that. So, here is an opportunity, market is growing, there is a big demand for polysilicon, we want to, there is no other person making it in India. So, we should make it is Atma Nirbhar Bharat and all that, we got stuck royally there. Okay. Now, other people worldwide, we looked at it, Hemlock is in US, Wacker is in Germany, and Chinese several people, they were building plants also, because they are also the same numbers. We are talking about India, globally if you take 7600 gigawatt, and if they say 1/3 of that to be converted, you can imagine the kind of silicon that is required. So, everybody thought this silicon thing is big daddy. So, we should really do something to hype up the capacity. So, everybody is thinking like us, we are also thinking like that. Now, for technology development, the key issue is, if you are going to do, you should do it somewhat better than others, then only you have a hope of doing something, right. Otherwise, always buy, if your job was to set up power plants, like buy wherever it is available, set it up, you will get power. Why do you have to develop something to do that? This is the issue, keep it in mind, but that is how it started. Now, this I will skip, I will put it there. So, the government also what they said is, in the value chain, if you see cell, first polysilicon, then lot of methods, then you get cell, then many cells are put into module, then blah blah blah, I said no. The government said that we want to encourage making it in India, because their thinking was, if everything has to be imported, we are in some difficulty. Suddenly if something happens in the world, then all your program will go fat, because everything you are just buying and setting it up. So, your program. So, they also felt that we will encourage anybody who wants to set up a manufacturing unit, come and ask me for something there, but the criteria is for a period of time till you become all right, that they were willing. Okay. They said that we will give you help, but You have to come out with a program and tell us I am getting involved in this. Initially I may be like this, like this, like this, like this. So, I need that support. After I reach somewhere else, I no longer need your support, I am like global competitor. So, that is what they said. So, during that period what they were willing to do is to make it a little easier, the raw materials if you wanted to import, they made it cheaper. The more and more finished product you are making it, they made it costlier naturally. So, that people who have start from raw material, so this is what it is they said. Now, this was the problem of our company, and now I am of course, I had always been a very good chemical engineer. I had also had a reasonable understanding of management practices. So, I went to this company when I was there, and when the company got highly hyped up. So, I told them, look, basically what we should do is, what we should do, we should be very clear. This all big picture is very clear. So, we have created a story that there is a big demand for solar energy, that solar energy can be met by several methods. In that there is something called polysilicon, that polysilicon is not made in India and we want to make it in India. Up to that story is very clear. Why is the question I raised. So, that management at that point of time said that your question is irrelevant. You are an engineer? I said yes. Can you build? Yes. Build. I said I am very happy to build. You are giving the money, I am not putting my money, I am getting a salary actually. But I just want to point out to you, are you clear? They said, do not ask these questions, just go and build if you can. I asked, should we build? Should anybody invest money to build a plant for making polysilicon?
Why not import it?
Yeah. So, I said, if this company is a chemical company, but I have to clarify that company. So, I said we are a chemical company, we make chemicals and sell chemicals. Some fellow is talking about global power, global warming, blah blah, etc. Program is going on and people are also buying, importing all this, setting it up. Why is that we have to take the extra trouble of going and making? Because now I will go back to the earlier thing.
Sir,
yeah.
when did you propose this idea? Timeline?
This story took place during 2005.
At that time, whether the perovskite had any effect on perovskite society had relative effect or something?
What is that?
Perovskite.
Perovskite, it was there, it was also going on. Luckily, we did not get into that. I have a big story for telling you that. Lots of fellows are tying, because the solar thing means everybody is wanting to, CO2 is a major problem, we should come out with this, dye sensitized solar cells, what have you, even quantum dots, it's going on. Point is, for a chemical engineers, this is a lesson which I want to say, because I raised this question, before any company wants to put money and developing something, you must be very clear in your mind why you want to do that. You must have something better than others, then only we should get into this, is my feeling. I got influenced all by this Harvard Business Reviews. So, but this company said, stop talking, can you tell me, can you build? So, I said it is a challenge. The thing is, there was no technology available, that was another reason, because usually in one of the classes we said, when you want to make something else, normally companies what they will do, they will go to somebody, pay the money, license fee, technology, buy it, install it, the whole package will come. So, this company attempted also. I later on learnt about it. So, before I joined, they had tried, and all this other fellows says that why should I sell technology to you, because it is a booming thing. There were only 4 or 5, like I said, Wacker, there is Hemlock in US and some Chinese companies. Everybody wants to take advantage of the market. Why will they want to give that know-how to another company to make and enter the market? They say no, sorry, we make more money on the product rather than selling on technology, which is very different from, if you want methanol today, you will get methanol technology, because nobody can have a monopoly on methanol. So, this is the key point that you have.
At that point of time, there was a monopoly for this
Technology.
But is it like
Even to this day it continues.
it continues?
Yeah, because it is, later on you will realize it is not simple. It takes about 15 years of dedicated effort to do it, and Chinese who are also starting from scratch did it. Our question to my company was, if you are clear in your mind, you are willing to, you remember one of the lectures I said that technology development is not for the light hearted fellows, acha, today we will do technology development, tomorrow coal field. So, I suspected, I said look, by the time I was fairly experienced in chemical industry. So, I advised this company, they took me for my technical capabilities. So, I said I am happy, but I also bring along with me business capabilities. So, take it or leave it is up to you, and they said leave it. How many times I have to tell you, please leave it, you are only there for technical capabilities. That is the story. So, the technology was not available. So, we put a team of together and then said we will develop the technology. Now, thing is like this. Yeah, what is the technology? Just few slides. I am just having to go back and forth on this because I did not come. Yeah, the process is, first you start with some silicon. So, what you start with is impure silicon, Si, but this has got lot of impurities. Now, how do you get Si? Go one step back. SiO2 all of us know, silicon dioxide, sand. So, basically everybody has to start from SiO2 universally. So, you start with SiO2, take some coke into that, coke, coal minus all impurities, because coal comes with its own impurities, right, ash content, that should not add up to this stuff, sand. So, you take practically carbon, 98-99% carbon, that is called coke. So, you take that carbon, sand, put it in an electric furnace, heat it, SiO2, that oxygen combines with carbon, CO2, Si remains. Of course, you add the quantity such that carbon does not remain back in this. So, that is called impure silicon. It was called metallurgical grade silicon, because the process of making is very similar to steel. Steel also, if you take iron ore, Fe2O3, you will add coke, heat it in the blast furnaces, all the oxygen of the iron gets converted along with carbon to CO2, and that hot iron you would have seen in how many videos, it is flowing out like that. So, it comes, it is called metallurgical silicon. Now, China was already into this, and they were making this metallurgical grade silicon at $2 a kg. Now, our question is, should I start from sand or should I start from metallurgical grade? Now, of course, who do I go and ask? Because if I go and ask the company, they says you are an engineer, go and build a plant. That was a standard answer. Many of you youngsters who are having this problem, I tell you this problem I faced when I was 50 years old. So, it is not an unusual problem. So, I said arbitrarily, okay, I know companies, finally when it comes to spending money they will be conjuice. Therefore, let me not go with too much backward integration, too much of money, and secondly, making a product of $2 is most likely to have much margin. This is my guesswork. So, I said let us start, anyway it is available in, it is still an imported product, but it is cheap product. So, I start with metallurgical grade silicon. So, it is impure Si. Then what you do, this plant was making PVC, and therefore, there was a lot of byproduct of hydrochloric acid gas, because in the process of making PVC you generate byproduct HCl. So, HCl and this silicon can react to form something called trichlorosilane, SiHCl3. This is the liquid. So, we are converting a solid into a liquid. Then this liquid can be distilled and purified to your Hartz content. That is the that is know-how, because the impurities of that silicon comes from, you have to go somewhere else. No? So, when you chlorinate it, all the impurities will get converted to their chlorine salts. For example, if there is parts per million level of aluminum, aluminum will become aluminum chloride. If there is parts per million level of iron, iron will become FeCl2 and FeCl3 and so on like that. So, you then take this impure liquid and distill it and distill it and distill it in high efficiency distillation columns, you get very pure trichlorosilane. This trichlorosilane is a funny compound. I will have to write like this, SiHCl, Cl, Cl. So, if you see, it is slightly asymmetric, right. If it was SiCl4, it is very stable, because silicon is surrounded by same atom in space. It is a tetrahedral structure like carbon tetrachloride or methane, carbon H like that. But if you take CH3Cl, which is methyl chloride, it is highly reactive because of the asymmetry. So, SiHCl3 is a highly asymmetric molecule, and therefore, can be decomposed. Next step what you do, you just heat the damn thing and then break these bonds, you get silicon. So, that is the process. So, we start with metallurgical grade, chlorinate it. Why? Because we want it in the form of a impure liquid from solid, distill it, you get purity liquid, break all those bonds, get silicon. That is the funda, and details of all this available. So, basically the process scheme as we thought through had a chlorination step where there is a solid gas reaction taking place, vapors are produced, you condense the vapor, you get the liquid, then there is a high efficiency distillation column. After that there is a cracking unit where you have to crack that. This is the chemistry process. This reactor is where we stuck. Imagine none of us, I had a team of I think about 3 engineers, young fellows like you, none of us had any experience on this, 0. All our thing was chemical engineers handbook, Perry, internet, search and got. So, all this information we searched and got. Then we went to IISc Bangalore. IISc Bangalore, this I am talked about 2003, right. IISc Bangalore in 1980, some research scientists wanted to work on this process. They have done something and kept it in some archives. We came to know about it, so we went and dug out all those papers and saw. They had noticed there is a 1950s patent of Siemens, the same electrical Siemens. They had a reactor like this. You can see it is a reactor where you already make some silicon. Imagine somehow somebody has given you pure silicon, that is a silicon in the form of a U. Now, silicon is semiconductor, so it will not conduct electricity under normal conditions. If you recall, one of the properties of semiconductors is as the temperature goes up, they will conduct more. Metals on the other hand, as the temperature goes up, they conduct less. This is the funda between the band gap and freely floating electrons. So, they had made advantage of this, the Siemens guys have done. You initially take this silicon, pure silicon in the form of a U tube, electrically heat it up. So, initially slowly you will heat up, but as it picks up, it will become more conductive. So, it will pick up more heat. So, it is a runaway kind of a reaction, so it gets heated up. This becomes very hot, glowing. At that conditions, our trichlorosilane, which we have purified and kept it there, push that into that reactor. So, there is a glowing hot solid of silicon onto which this SiHCl3 is hitting. On the surface, this breakdown takes place and the silicon stuck on the solid. So, these rods slowly grow bigger in size. It is a funny thing. This is the reactor outside view. This is how that rod. Initially when you start with, it will be something like 1 inch thick, more like a large diameter wire, and then as the reaction takes place, it becomes bigger and bigger. The beauty is, if it becomes bigger, area of cross section is increasing and therefore more current it can draw, it can get even heated better. That is one part. Then at the end of it, when you grow sufficiently big, now I will go back to Y150. Beyond 150, if you try to grow, the whole thing collapses and falls. You can imagine this kind of a structure, it will buckle and fall. So, there is a certain limitation beyond which it cannot be grown. Then you take it out, cool down the reaction, do everything there. This is no ultra pure, because it has been atomically broken down to silicon atoms and then one after the other, and you crush it, you get this. This is still polysilicon. You have to again remelt it and recrystallize it, you get this. So, this is the process that we read and we wanted to build a reactor. So, lot of interesting things we did. In fact, as an engineering thing, for 4 guys who had no experience excepting strong chemical engineering, in 18 months we built that reactor to 25 tons per day capacity, ran it, we got the product, we sent the product to US National Research Laboratory. They said it is acceptable quality for photovoltaic grade. It was not still meeting electronic grade, and promptly the whole plant was scrapped because it was not economical to make. So, after 24 months we came and to the conclusion, oh, in this method of making we are not able to compete. Product is successful, of course you did a project, quality was coming, product quality is all right, you are getting output and all that, but the cost in which we were making it was just not possible for us to compete in the world market. So, the question was why other guys are able to make, we are stuck. So, this question I went back to our company and said, look, you wanted it to be made in 24 months including planning time, we got it. Now, you find this is the cost, but this cost, yeah, that is the cost, and I know the breakdown of where the cost is. I will show you where the cost is. This is how it came. So, biggest cost item was electricity, because when we were heating up that stuff, what happens is we put something there, there is a heat loss, because the temperatures we are talking about is about 1100 degrees Celsius for those silicon rods. At 1300 it will melt, silicon's melting point. So, you have to keep it very close to that temp. What happens is the heat loss through radiation is horrendous, because that heat loss is T power 4 minus T power 4 into area into sigma. Now, sigma is Stephen's constant, so that is remaining the same. 1100 degrees is 1100 degrees, start of the process also, end of the process also, but the area when you started with 1 inch, 2 inch initial seed crystals, area was pi dl, surface area, right. When it became 150 and all that, it is some 10 times. So, as the process goes, you are spending more and more energy on radiative losses. So, the Siemens process 1950 patent. So, obviously, we went and found other guys are making from Siemens process or what, we do not know, because nobody will tell us. Then bits and pieces commercial intelligence comes, you are watching Siemens process, ha 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 ha, everybody is laughing. Why? You had high energy consumption. Clever guys who started 15 years behind, they also went through this, but that time competition was less, they got away. But as more and more people are coming, they spend time, they dropped this process and went to fluidized bed process. The advantage of fluidized bed process in one line, then I will stop, is in this case what happens, you take a single rod, it is radiating heat like mad, from where, imagine there is a rod here, there is another rod here, there is another rod here. So, we went for a 3 rod, because 25 tons capacity, our thinking is always small, 1, 2, 3. Now, this one rod, a portion of this rod will see another rod at the same temperature, therefore, there is no heat loss. This transfers heat there, that in turn transfers heat here, but 3/4 of this rod is facing reactor walls and is at lower temperature. Reactor walls cannot be at 1100, so it takes away the heat. That is the fundamentally why it is energy consumption is very high. In fluidized bed reactor, you can imagine the number of small particles, 100,000, excepting for those particles which are on the periphery of the reactor, all of them are seeing each other, right. If I put it like that, it is so simple, we should laugh, and actually we should take a stick and beat us for doing this Siemens process. If why did we not think of a fluidized bed reactor in the beginning? So obvious, because in a fluidized bed reactor, imagine what is happening, all these things are particles are bubbling, blah, 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 it's happening. So every particle which is inside the core is surrounded by other particles. So it cannot lose heat, because if it loses heat to the next particle is also at the same temperature, fluidized bed excellent temperature control. So it will be out of the total volume, which is pi d square equivalent, only the one which are on the periphery, which is pi d, is facing a colder temperature. So the energy consumption is drastically less, and those particles also grow. The same thing, you fluidize with smaller particles, add a trichlorosilane purified process, it will deposit, particles become bigger and bigger, but still they are fluidized, still they are. So against 800 kilowatt hour per kg of product, they got fluidized bed 90 units of power. So you can imagine the difference is 700 units, 700 units multiplied by whatever is the power cost, that is the difference. So this unit was, so the summary and the learning is, before we plunge into technology development, there is a dilemma, because as engineers, like my case was a typical case. In spite of my very long years of experience in different positions in company. This particular company with whom I worked chose to ignore my totality of knowledge. They said you do this. In their mind there was some senior guy who was the owner, we will see, that kind of a confidence. But this is slowly, we will see what same physics, same thermodynamics, same reaction engineering is true for the world. So, unless you do this, like I said, technology development, now go back and say 3 things are required. I said your level of understanding of the basics should be the highest of all that compared to the job in manufacturing. This guy is basically a manufacturing guy. He has been successful businessman doing stuff, conventional stuff for 40 years. So, his mind is strong in basics reasonably, so on. The slightly higher level of technical thing should be in EPCM companies, because you are going to talk about interaction. The biggest one should come from thing. Plus business understanding of what is the world going, where is it going was 0, and that is really most of the time it is true in Indian companies, because they are not developing this globally, where we talking about globalism is easy, but you have to have a feel of human beings all over the place, they are all sort of pushing, pulling, where do I figure out, that is a key. So, technology development, if you really want to go, this example is a great example of very good technical efforts failed because the key issue of what is that. See, if you look back what we did, we had no idea. So, we went and did some study, we took some patent, something is working, we did, tried, successfully, came out, but we never put that picture in a screen and say, okay, I am doing like this, I am doing, other guy is also doing. I mean, what is the benefit I got out of this? What is that I have done differently? You know, in the technology development, when I ask you to do, ask you to take the existing one, then say look for incremental, where is an opportunity, that is a key step. You must get the gut feeling of I must do something, then I will get a hold on, you will get a hold for 5 to 10 years, because other fellow will quickly, patents anyway will run off, there is no meaning in patents, enforcement itself is a big issue. After quickly the other guy, in this case they kept it secret for 10-15 years successfully. In that 10-15 years we were idiots not getting to know what was happening. That is the example I gave of failed technology development, just to emphasize the point. You must have, for serious technology work, if you are going to think of, you should be very good in your subject, that is taken for granted. You must also have that acumen, what is that I am going to do very differently compared to the other guys who are also equally clever. Cannot be hype, acha we will see, Indians, you know, we are all jugaad hai, oh kuch karenge, we will do. How many times you hear, na, acha Indians, yeah, something we will do, do not worry, oh, we will, what will you do? Science does not work like that, you must have some solid understanding of how it works. So, that step 24 months, I am also a guilty party. I can only claim saying that acha my bola, I told you, that is all, but finally it was a failed effort. We spent about 25 to 30 crores on this. I am okay. Other 3 guys, good news is because they worked so well and picked up, each one of them got picked up by a foreign company which was working in this area. Acha, what did you do? You built a polysilicon plant? Come. They were very happy, because for them getting person with this kind of a thinking, dedication is a is a good, and they are supported by top class thinking at the top management. You know, those guys knew, like I said, you know, for 20 years they spent their life in that business. For them it is a very good combination. Here is somebody who has prepared the raw material for them, come and join, take. They write even to me saying that, sir, you remember what all we did, like that. So, sorry, I took a longer time. So, that is what I will do, and tomorrow what I can do is hydrogen I will avoid. Tomorrow what shall we do, because you know now more and more is going to be making use of what you have, how to apply in a given situation there. So, I will check with Nagarajan what he wants to do like that, and then we will probably take equally a different technology thing, which is on a more like a lab scale just as a emerging technology kind of example.